Unit 1, Relativity, Lecture 2. This lecture is about the relationship of frame transformations and physical symmetries. Symmetries are a very important concept in physics. In fact, some people say that physics is really the study of symmetries in nature. In the last lecture, we described frames as mathematical conventions that we use to quantify physical concepts. How can frames then tell us something physical about the universe? It turns out that if we use frames to represent the universe through mathematical expressions, then the way those mathematical expressions change with a frame transformation can inform us about symmetries in the universe. That's what we're going to see in this lecture. First of all, it turns out that there are two kinds of physical symmetries that one can study. One is a symmetry that has to do with the physical arrangement of objects and matter in the universe. We can describe this physical arrangement with mathematical expressions, and we can study what happens when a transformation takes place. Symmetries that are discovered through this mechanism are called extrinsic symmetries. There's another kind of symmetry that is found out by looking at what happens to mathematical expressions that express the laws of nature. What happens to them when we transform the coordinate? Symmetries that are discovered through this mechanism are called intrinsic symmetries. The two kinds of symmetries are quite different from each other. Extrinsic symmetry of the universe is manifested through the structure and content of the universe, while an intrinsic symmetry of the universe is manifested through the laws that govern the working of the universe. Since space is modeled after a rigid body, it would be interesting to see what these symmetries mean for a rigid body. Extrinsic symmetry in a rigid body can manifest itself in several different ways. One example, which is given here, is if the atoms that make up the rigid body are not spherical, but they have an elongated length in one direction. This will give rise to a lack of symmetry in that direction. Similarly, if we have a rigid body that is much thinner in one direction than in the other, that can also be considered to be a physical extrinsic symmetry. Now, what would an intrinsic symmetry inside a rigid body look like? Well, in a rigid body, you can have propagation of waves, which have to do with the properties of the atoms that make up the rigid body. If we found out that the speed of these waves is different in different directions of the body, that would be considered an intrinsic symmetry of that rigid body. Now let's see how frame transformations can be used to reveal these physical symmetries. If a frame is used to construct a description of the distribution of matter in the universe, and if as a result of a frame transformation that description does not change, then we say that we have an extrinsic symmetry in those dimensions. Here on this slide, we have an example of what a frame transformation would do to the description of the solar system. We know that the solar system is not the whole universe, but for this example, we're going to make that assumption. If that is the case, then it's easy to see that if we make a rotation of this frame in the xy plane, the description of the solar system pretty much remains the same. But if we make a rotation that involves the z-axis, then the description of the orbits of the planets will become a lot more complex. Unlike a geometric symmetry, a physical symmetry simply implies that there is no preferred frame in the dimensions that we are considering that symmetry. Now let's look at intrinsic symmetries. When a frame transformation does not change the form of physical law that is expressed in that frame, then we say that we have an intrinsic symmetry with respect to that physical law. And if this is true for all physical laws, then we say that the universe is intrinsically symmetric for that transformation. A good example to look at is Newton's second law, F is equal to ma. It can be shown fairly easily that F is equal to ma is invariant under both translations and rotations in space. So this would tend to indicate that our universe may possess an intrinsic symmetry under translations and rotations. In general, the presence of an intrinsic symmetry implies that all the frames with respect to that transformation are equivalent in describing how nature behaves. A natural question to ask is how the two symmetries relate to each other. It turns out that intrinsic symmetry is the stronger symmetry between the two. What this means is that if there is a transformation under which all of the physical laws are invariant, then it is likely, but not essential, that the universe will also show a structural symmetry in those dimensions. Since the universe evolves through the laws that govern the universe, it's a good question to ask how an intrinsically symmetric universe can become extrinsically asymmetric. There's a couple of different reasons why this can happen. One is that the initial conditions that started the evolution can have a bias, which can create an asymmetry, or there is something called spontaneous symmetry breaking, which can happen during the evolution of the universe and can result in the breakdown of an intrinsic symmetry as it expresses itself in the content and structure of the universe. There are two other terms that we need to define in the context of symmetries. This is the distinction between absolute and relative concepts. A physical concept is said to be absolute if it does not share a symmetric relationship with another dimension of that concept. This can be with respect to extrinsic or intrinsic symmetries. Similarly, a physical concept is said to be relative or to have relative significance if there are other similar dimensions with which it has a symmetrical relationship. Again, this can be for extrinsic or intrinsic symmetries. Now, our example of the solar system that we considered earlier illustrates these terms quite well. For the frame that we have in the solar system, the z direction can be said to be absolute because it does not have a symmetry with either the x or the y direction. On the other hand, the x and y directions can transform into each other and still retain the symmetry of the solar system. So these two directions are said to be relative to each other. We conclude this lecture by describing two extrinsic symmetries of our universe. The first one is homogeneity. What this means is that if we go to larger and larger scales, and in this case, the scale that you have to go to is measured in hundreds of billions of light years. At that scale, the universe looks the same everywhere. In other words, it is translationally symmetric. Another symmetry that our universe has is called isotropy. What this means, again, is that when we go to larger scales, the distribution of the matter in the universe is the same no matter which direction you look into. And this is obviously the rotational symmetry possessed by our universe. As a matter of fact, these principles are held with a fairly strong belief, and they have been elevated to a principle that we call the cosmological principle, which states that the universe is both homogeneous and isotropic at large scales.